Hi everyone. Today we start one of the most important chapters on ship stability, that is the trim. So I will go through some theory part of it, and then there will be numericals. There will be few videos because there will be at least 4 or 5 numericals of different types. So let's begin with the concept, the theory, which will help in doing the numericals. Trim is also the called longitudinal stability. When we are studying trim, we are actually studying the longitudinal stability of the vessel. There is transverse stability, and there when we deal with the list GM, transverse GM, and transverse KM, GZ, that all comes in the transverse stability. This one is this is longitudinal stability where we are also again we have the Km and Gm, but longitudinal Km, KML, and Gm also longitudinal Gm, GML, then Bm also longitudinal Bm, BML. So in transverse stability, you studied transverse Bm, transverse Gm, transverse Km. The same uh, things are here, but longitudinal. Longitudinal GM, longitudinal BM, longitudinal KM. So we are now studying the longitudinal stability or the effects mainly on the ship's trim. And trim is nothing but difference between forward and aft draft. So basically we are going to find the trim and the drafts forward and aft due to loading and discharging, shifting. So the basic theory, let's see this figure here. You can see a ship on even keel. Okay. The ship is on even keel, means forward and aft drafts at center of flotation all are equal, same draft everywhere. Ship's center of gravity is directly above on the center of buoyancy. So in other words, if we take distances from aft perpendicular, so distance of the center of buoyancy from aft perpendicular called LCB, longitudinal center of buoyancy, and distance of the ship's center of gravity from aft perpendicular is called LCG, longitudinal center of gravity. AG is the distance of the ship's center of gravity from keel, that is kg, and this is from aft perpendicular along the length of the vessel, fore and aft direction, that is LCG. So if the ship is on even keel, you can see LCG is equal to LCB. Both distances from aft perpendicular are same, equal to each other. So if the ship has to float on even keel, the LCG must be equal to the LCB. LCB is easily available against draft or displacement in hydrostatic particulars. LCG we have to calculate. And then we see that what is the difference. If they are different, then we can come to know the ship is going to trim. And now depending upon which is bigger, LCG is bigger or LCB is bigger, the ship will trim by stern or by head. So on even keel, they are same. They are always, when the ship's floating at even keel, if you extract LCB at that particular draft, hydrostatic draft from hydrostatic particulars, that will be the LCG also of the vessel. Okay, now let's see these two figures. The first one. Now due to some weight, loading, discharging or shifting of whatever can be the reason, loading, discharging, shifting of some weight, the ship's center of gravity G has shifted aft. So you can see now there is a difference between LCB and LCG, which is equal to BG here. You can see BG. This BG is nothing but LCB minus LCG. Center of gravity because of weight has shifted aft, creating a lever which is called trimming lever. Trimming lever is that this length BG, and you can see that LCB is greater than LCG here. So if LCB is greater than LCG, what is happening? The force of buoyancy is acting upward, shifts weight from gravity acting downward. Both are forming a couple, and it is easily can be visualized that this will rotate the ship by stern. Trim will be by stern. So the ship, this kind of a couple where LCB is greater than LCG, the ship will rotate by stern and the ship will trim by stern. This lever LCB minus LCG, which is equal to BG here, this is that lever BG, and is equal to LCB minus LCG. This is called trimming lever, because what is the now moment here? Trimming moment, weight multiplied by distance. So it's a couple. So couple means any force which is weight here shifts displacement multiplied by the distance BG, which is LCB minus LCG. So the trimming moment will be shift displacement W multiplied by the trimming lever LCB minus LCG. Now in another scenario, if the ship's due to weight distribution, fore and aft weight distribution, if the ship's center of gravity shifts forward, you can see the LCG is now LCG is greater than LCB. Okay, you can see LCG is greater than LCB. Trimming lever is again BG. This is the trimming lever between them. So this couple, you can easily see how is this couple going to rotate the ship. It's going to rotate the ship in a clockwise direction, means you will be trimming by head. The ship will trim by head by this couple. So if LCG is greater than LCB, you will have trim by head. So in this, when the ships are trimming, the ship will keep trimming by head or by a stern until the time the center of buoyancy will also shift and come directly under the center of gravity, and then she will be in static equilibrium. So in this case, if the ship trims by head, the underwater volume in the forward direction will be more, and obviously the center of buoyancy, being the center of gravity of underwater volume, will shift forward, and the ship will continue to trim until the center of buoyancy will directly come under center of gravity, and this trimming lever BG will disappear, and the ship will be then in equilibrium. This is the main theory about the trim chapter. Okay, trim is difference between forward and aft draft. The ships don't trim about midship. If the ship is trimming by stern or by head, and if we assume that, oh, it must be trimming about the midship, then it's not true, because the center of flotation is the centroid of the water plane area, and it is not rectangle. On a ship, it is not a rectangle. So depending upon where is the centroid of the water plane area, it may be forward of midship, it may be aft of midship at certain drafts. So the ships trim about center of flotation. shifts trim about the transverse axis passing through center of flotation. So as I just now explained to you, what is the trimming moment? The shift displacement W multiplied by that lever, trimming lever BG, which is LCB minus LCG. So trimming moment is shift displacement W into LCB minus LCG. Total trim, the final trim after loading, discharging, or shifting of weight has taken place. The formula for the final trim is LCB minus LCG into W, which is trimming moment. As you know, this is trimming moment, and trimming moment divided by MCTC will give us the trim. This trim is in meters. Okay. Now, since this trim which we find by MCTC will be in centimeters, but we have to divide by 100 to get it in meters. So the answer will be in meters. The answer of this trim will be in meters. But if you are wondering why we are dividing by 100, because whenever you use MCTC, which is moment required to change trim by 1 centimeter, the answer will come in centimeters. So if you want the answer in meters, then you divide by 100. If you don't divide by 100, you will get trim in centimeters. That's all. That is the only difference. But we divide by 100 and we get the trim in meters. If you don't divide by 100, it will be centimeters. So once how do we proceed in questions which are where the hydrostatic particulars of a vessel are given? First thing, we find the final displacement. Okay, we have the initial drafts, initial displacement. We find out how many tons of cargo we have to load or discharge, so we get the final displacement. Against the final displacement, we enter hydrostatic particulars and we get the hydrostatic draft. Remember, the hydrostatic particulars are given for salt water, especially this example here in ship, question on in ships. But mostly all hydrostatic particulars of a vessel will be given for salt water. So there you have to be careful that when you are entering the hydrostatic particulars is for salt water, the ship floating in salt water. So there is a way how to get, we will see that later on, how to get the actual hydrostatic draft if the ship is not floating in salt water. If the ship is floating in salt water, you get straight away the hydrostatic draft. Otherwise, we have to make corrections for the density. So once we have the hydrostatic draft, against that final hydrostatic draft, we find the LCB, MCTC for the ship's final condition. And in this formula, you enter LCB will be the final LCB, MCTC will be the final means for the final sailing draft upon completion of the cargo operation. What is the departure draft? That hydrostatic draft. And W will be again the same final displacement. And we will get the actual trim of the vessel in final condition, not the change of trim. This formula will give the actual trim. So once we have the hydrostatic draft, then we extract LCB, MCTC, and we get the trim. This when you have divided by 100, so it will be in meters. After the trim, we calculate forward trim and aft trim. What will be the change in draft forward and aft? And that will be trim into LCF upon LBP. LBP is length between perpendiculars, and LCF also you will extract from the hydrostatic particulars. When we are taking out LCB, MCTC, same time you can extract LCF also for this hydrostatic draft, because it will be required here to calculate TA. Trim aft will be total trim into LCF upon LBP. Trim forward, there are two ways. You can subtract TA from total trim, like this here. From total trim, you can subtract TA, you will get trim forward. Or you can also do like this here. Total trim multiplied by distance of the forward perpendicular from center of flotation. And that will be length between perpendicular minus LCF. So total length, and if you subtract the LCF, you will get the distance of forward perpendicular from center of flotation. This can give also the forward trim. Or you can do this. Total trim minus aft trim also will give forward trim. And likewise, if you have the forward trim, then you can subtract from total trim, the forward trim, you will get the aft trim. It's the same. So this will be the general flow of the question. First find the hydrostatic draft, then find the displacement, final hydrostatic draft, get the final LCB, MCTC, LCF, then the trim, and then find TA and TF. Now this TA and TF will be applied to the hydrostatic draft. So if you can, as I explained to you, if LCB is greater than LCG, you will get positive answer. That means trim is by stern. So aft draft will be more than the hydrostatic draft. So you will add TA you will add to the hydrostatic draft to get the aft draft, and TF you will subtract from the hydrostatic draft to get the forward draft. And if the trim is coming in negative, obviously LCB is smaller than LCG. Then trim will be negative and it will be by head. That indicates that trim is by head. So in that case, you add TF to the hydrostatic draft. Equal forward draft will be greater than the center of flotation, and TA will be then subtracted. Hydrostatic draft is draft at center of flotation. To obtain aft draft and forward draft, we apply TA and TF to hydrostatic draft. MCTC, LCB and LCF for final displacement to find final trim. Let's see this small derivation of how we get the formula for TA, which is trim into LCF upon LBP. I will zoom it so you can see this diagram very clearly. So here is a vessel which is trimmed by stern. This is the water line, the blue one, and you can see aft draft is greater than the forward draft. It's a trimmed by stern vessel. F is the center of flotation, and the distance from the keel from center of flotation I have marked. This is a hydrostatic draft. This is a hydrostatic draft because it is at center of flotation. So from center of flotation to aft perpendicular is LCF. LBP is the length between perpendiculars from forward to aft. Now if you see this diagram clearly, you will see that there are two triangles we are comparing. One is the big triangle A, C and D. So CD is the length between perpendiculars and AC is trim by stern. You can see that this is aft draft minus forward draft, the remaining is trim. So this is, I put in green T, this is a trim. So the side of this triangle ACD, side AC, which is perpendicular, AC is nothing but trim. And the small triangle, you can see ABF, the small triangle. They are similar. Obviously, they are similar because they are all angles are same. So for similar triangles, ACD and ABF, if I take the ratio of their sides, then AB upon BF, AB upon BF is equal to AC upon CD. So small triangle is ABF, AB upon BF, and the big triangle ACD, AC upon CD. They are in the same ratio. And AB is what? Now here, you can see this AB, this is AB. If from updraft, I subtract this correction AB, I will get my draft at center of rotation. See, I have drawn this red line is cutting here at B. So from B to the keel is the draft at center of rotation, which is hydrostatic draft. So if the ship is trimmed by stern, then from updraft, subtract correction AB and you will get the hydrostatic draft. So AB is the correction to updraft. BF is nothing but distance of center of rotation from off perpendicular, LCF. AC is the trim and CD is the LBP. From here you get correction to updraft will be equal to trim into LCF upon LBP. So correction will be subtracted from updraft, which is very clear here. See, updraft minus correction AB will give me the draft at center of rotation if the ship is trimmed by stern, and if the ship is trimmed by the head, you add the correction. You will get the draft at center of rotation. If the ship is trimmed by head, then this correction which we find, you add it to the updraft. Trim into LCF upon LBP. Now another important term here is MCTC when we are dealing with trim questions. It is when you are having the hydrostatic particulars of the vessel, you don't have to worry about it. It is given against the hydrostatic draft in the particulars. As you must be remembering that the MCTC is also affected by the density of water in which the ship is floating. MCTC from the hydrostatic book will be for salt water. You must correct it for the actual density in which the ship is floating. Same like TPC. Whereas LCB, LCF, they are unaffected by density because they just depend upon underwater volume, water plane, shape and all, not on the density. So they remain unaffected by the density. They can be straight away picked up from the hydrostatic particulars against the hydrostatic draft. So let's see this diagram. Here's a vessel which is trimmed by the head. Okay. Why? Because there was a weight W in the aft part. This W has been shifted by a distance D to the forward part. Obviously, the ship's center of gravity G, which was on the center line, has shifted parallel to the weight to G1, thereby creating a trimming moment W into GG1, and the center of buoyancy, which is on the center line, will have to come under the new center of gravity for the ship to be in equilibrium. So ship will start trimming by the head until the time the center of buoyancy will continue to shift and will shift to B1 when it will be directly under G1 shift center of gravity, and the trimming lever will disappear and ship will be then at equilibrium, static equilibrium. So here also, if you see that this there are a big triangle which is covering the length between perpendicular and the trim of the vessel. T is the trim of the vessel and LBP. So if you see this triangle and a small triangle here, GG1 ML. ML is longitudinal metacenter. So since it is right here in front of you, I will tell you what is this. So when the ship trims by head or by stern, the center of buoyancy shifts out, like from here B to B1. Now if I draw a vertical from center of buoyancy upward, it will meet the center line of the vessel at ML, which is longitudinal metacenter. Okay, and from G to ML is GML, longitudinal metacentric height. B to ML is BML, which is metacentric radius. It's called longitudinal metacentric radius, BML. So see the small triangle GG1ML and the big triangle here, which is formed by the trim and the length between perpendiculars in blue lines. The angle theta is the same because the angle formed between the two water lines when the ship was floating earlier on even keel and now trimmed, the angle formed between the two water lines is the same, which is the angle formed between the two verticals. So both are, now if I, in the big triangle, I divide trim by LBP, it is tan theta. Whereas in the small triangle, GG1 upon GML is also tan theta. So trim upon LBP is equal to GG1 upon GML, both are equal to tan theta. And you know the trimming moment is W into GG1 is equal to also weight which was shifted by distance D. In this case, it was weight was shifted by distance D. So small w is for the weight which was shifted and D is the distance by which it was shifted. So small w into D is the trimming moment, which is equal to W into GG1, which I showed you earlier. The actual trimming moment after G has shifted the couple is W into GG1 is equal to W into D. So that means GG1 is equal to W into D upon displacement, capital W. So in this number one, I can trim upon LVP is equal to GG1 upon GML. Here I can insert the, in place of GG1, I can write W into D upon displacement. Capital W is displacement, small w is the weight. So trim upon LBP, T upon L equal to GG1. In place of GG1, I write W into D upon capital W and GML. So this number one formula is rewritten, T upon L, and we insert the value of GG1, which is this W into D upon displacement, capital W. So if I assume that this trimming moment W into D, which is a trimming moment, the weight has caused by shifting of the weight. If this trimming moment causes a change in the trim by 1 centimeter, then this T, which is a trim, will be 1 centimeter. Change in the trim is 1 centimeter. We can write it by like 1 upon 100 because this T upon L is in meters here. This is in meters. So if I write 1 centimeter, I will have to write 1 by 100. So it will be 1 by 100 L. And the trimming moment W into D, which causes change of trim by 1 centimeter, it can be written as MCTC, which is nothing but moment required to change the trim by 1 centimeter. So in place of trimming moment W into D, I can insert MCTC because I am assuming my change of trim is 1 centimeter. So the formula then becomes T upon L is equal to 1 upon 100 L is equal to MCTC upon displacement W into GML. So in place of T, I have put T is 1 centimeter, so I put 1 by 100, and in place of W into D, which was streaming moment, I put MCTC because MCTC is the trim required moment required to change trim by 1 centimeter, and GML stays like that. So this formula rewritten becomes in this manner. So MCTC we found W into GML upon 100L. If GML data is not available and you cannot calculate GML, we can use BML in place of GML. They are approximately very close to each other because BG is a very small distance compared to GML and BML. BG is very small, so it can be safely used. For example, if you have a box-shaped vessel and the rectangle water plane is a BML can be calculated and MCTC can be found if you cannot get GML. What will be GML? GML will be KML minus KG. KML minus KG of the ship. So if GML cannot be found, we can found the BML. And sometimes the question is giving you water plane area is a rectangle or it's a box shaped vessel. So KML is equal to KB plus BML. And BML, longitudinal BM, is IL, which is longitudinal second moment of water plane about center of flotation upon ship's volume of displacement V. So IL for box ship vessels can be calculated. There's a formula for if the box ship vessels or in fact if the water plane is a rectangle, then IL is given by BL cube upon 12. Remember, it's only if it's a rectangular water plane, means like it's a box shaped vessel kind of, then you can find the second moment of water plane longitudinal. Now remember, there is also a transverse second moment of water when we are dealing with the transverse stability. There it is LB cube upon 12, but in the longitudinal IL will become BL cube upon 12. So the length will be cubed here. Length L is the length of water plane, B is the breadth of water plane. And for box ship vessels, okay, BML is equal to IL upon V. V is the underwater volume of displacement. So that will be length into breadth into draft for a box ship vessel. So the formula becomes BL cube upon 12 into L B D. D is the draft. So if you cancel out, it will become L square upon 12D. The square of the length of the water plane. L is the length of the water plane. Square of that. D is the draft. So once again, it's for box shaped vessel, not for the actual vessels. Only if the vessel is a box shaped vessel, you can do this. You can find BML by formula L square upon 12D. And you know, if the box shaped vessel given is on even keel, then KB will be half of the draft. So then KML can be found by KB plus BML. Final LCG. You remember the trim formula? LCB minus LCG into displacement upon MCTC. Okay, this trim formula. So we talked about LCB, MCTC final displacement from particulars, and also LCG in the final trim will have to be final LCG. So how do we find the final LCG? We take moments from after perpendicular. Okay, weight multiplied by its LCG gives the longitudinal moment. And remember, when you are doing this, finding the LCG by this method, do not ignore or forget to include the initial displacement of the vessel and initial LCG. Initial displacement multiplied by initial LCG in the given condition of the vessel before the operation is done. That has to be also taken into account. So multiply the initial displacement, original initial displacement by the initial LCG and get the longitudinal moment. Write the moment here. Then the weights loaded or discharged multiply by their LCG. You write their moment. If the weight is shifted, you have to multiply by the distance by which it was shifted and write its moment. Algebraic sum of all longitudinal moments divided by final displacement will give final LCG. Okay, it's the algebraic sum of all longitudinal moments, means if the weight is loaded, longitudinal moment is added. If the weight is discharged, longitudinal moment is subtracted. If the weight is shifted, if the weight is shifted forward, you add the longitudinal moment, which will be weight shifted multiplied by distance by which the weight is shifted. So this will be the longitudinal moment for the weight shifted. It should be added if the weight was shifted forward, and it should be subtracted if the weight is shifted aft. From its present location, if the weight is shifted towards aft perpendicular, then we have to subtract the moment, longitudinal moment, and if the weight is shifted towards the forward, means it's going away from aft perpendicular, then the longitudinal moment should be added. And then get the algebraic sum of all longitudinal moments divided by final displacement, we give final LCG. Sometimes in some questions, what I wrote here, initial displacement into initial LCG, which is very important that you must not forget. Suppose initial LCG is not available. If it's a Hinship question, one of the condition is given, then you go into that condition and you can find the LCG and even the longitudinal moment also available straight away. But if the condition is not given and only drafts are given, then in that situation, you need to find initial LCG first. So this formula for the trim is equal to LCB minus LCG into W upon MCTC is a trim. Here, if I instead I put the initial trim of the vessel in place of total trim, I can put the initial trim. They have given you drafts forward and aft. You can find the trim. So if I put the initial trim and the initial displacement, because you have the drafts, you can find the initial hydrostatic draft and you can find the initial displacement. Against that initial displacement, I can get the LCB and MCTC. So initial trim, initial LCB, initial MCTC and initial displacement I can put here in this formula and get the initial LCG. So all initial conditions can be inserted and find the initial LCG. Okay, if initial LCG you cannot get, that initial LCG will have to be found like that and then used here, multiply by initial displacement and get the longitudinal moment to find the final LCG. And that final LCG will be used in the trim formula for getting the final trim and final drafts. Okay, so I think I have covered everything about the trim chapter theoretically. So when we do the questions, I will keep reminding you of the what we studied here. So it will be all easily. So you got some idea of what we are going to do when we calculate trim question. This is basically kinship problems where the hydrostatic particulars are given. Because there it is important that we use the we don't assume thing that MCTC and all is constant, because it has to be taken for the final draft then. Okay, thank you very much, and wait for my next video. It will be, now I will start putting 3-4 videos one by one on trim questions from past papers. So the first one will be the question I've seen many times repeated. The vessel is on even keel in fresh water and it sails out. What will be the drafts in the salt water once it is sailed out in the open sea? So that will be the first question. Right, thank you very much.